Let us start lecture 40. The course is on phase diagrams in single component and binary systems, and today's topic will continue our discussion on isomorphous phase diagram. And today we will try to assess the fraction of solid and liquid solutions if we take any composition which is falling within the I zone at a particular temperature. Okay. Because we could see that few informations we can gather at what temperature and composition we get solid solution, complete solid solution, where we get a single phase liquid solution, where we get a mixture of solid and liquid solutions. That information we can get out of isomorphous phase diagram. And we have also seen how we could draw it from free energy composition diagrams. And the another one what we will do, we have shown it with schematic variations of free energy composition plots of solid and liquid solutions. Now, we will do it with by formulating equations, and by solving those equations we can also get isomorphous phase diagram. So, that calculation, how to calculate phase diagram using simple thermodynamic data, and what are those simple thermodynamic data which can be experimentally found out. And the experiments what we need to carry out is basically called differential scanning calorimetry or called DSC. From that we can get melting point information of both the pure components, as well as we can get enthalpy of melting for both the pure components. So, these two informations will be required to draw a complete isomorphous phase diagram. So, that will start today. But let us see what diagram we got. Remember, we will keep our assumptions that the melting point of B is always more than the melting point of A for our entire discussion. Okay. So, now here what we have done, we have drawn isomorphous phase diagram. Isomorphous phase diagram in case of binary ideal solutions, solid and liquid, and here the components are A and B, that are two metals, XA and XB basically the mole fractions of N and B, and that has been chosen in such a fashion that it leads to 1 mole of solution. Okay. And we are keeping temperature and pressure constant for each drawing of free energy composition. So, the only thing is pressure would always remain constant, and at a particular constant temperature, that constant temperature will change over temperature composition plot, and each temperature we will be seeing the equilibrium between two phases, and that gives us this isomorphous phase diagram. So, pressure is always remained 1 atmosphere, and temperature, the fixed temperature would change. So, once we change the temperature, so that temperature remains fixed. So, that is the concept of fixed temperature. Okay. So, once we do that, our diagram look like this, which is temperature composition plot. This is XB, pure B, pure A this side, and the diagram look like this, widen like this little bit. So, this is Tm A, melting point of B, and here we have temperature axis and the composition axis. This particular line called liquidus, this particular line called solidus. Below that line everything would be solid, above that, below that solidus line everything would be solid. So, that means solid solution, and above liquidus line everything would be liquid solution, and in between you have solid plus liquid, both will coexist, but of a particular composition. So, those informations we got. So, in fact, we can actually sense, for example, let us say I take a composition at this location let us say I take a composition like this. Let us say this composition is as per this is C0. Okay. Now, we can change the composition axis, we can change it to weight fraction of weight percentage of B. Okay. Instead of A mole fraction, we can change it to weight fraction. In fact, mole fraction to weight fraction you can do if we know atomic weight of A and B. Okay. So, now once we do that, if I take a temperature, let us say I take different temperatures. So, those temperatures are like this. So, let us say this temperature, and at Tm this is another temperature, this is another temperature. Okay. So, let us say this Tm is here, this one is here, and this is one temperature, this is another temperature. Let us say this is T prime, this is T3, or you can say TL liquidus, and this is T solidus. Ts and TL are basically solidus and liquidus, or liquid I can say solidus, fine, solidus. And then another temperature we are taking, which was T2, and this was another temperature which was T1. Okay. Let us see all those temperatures, what would be the phases as well as composition that can appear in a system. And those are the information we can actually get out of phase diagram. So, at T3 composition equal to C naught. So, that gives us liquid solution of composition C naught. TMB, if the temperature is TMB, C equal to C naught. So, those points, let me just put it in red color. These are the points I am considering. This is the point I am talking about. This is the point, okay, at C naught. So, that again gives us liquid solution of composition C naught. Now, at T liquidus, this is interesting. At that point, we will get the first solid to appear at that composition. If I extend this line, we get a solid of this composition and liquid of this composition. Okay. So, we will see at T naught C equal to C naught at liquidus, T equal to liquidus, we will get solid solution of composition. Let me that composition is CS1 and plus liquid solution of composition C naught. So, there I have to just show you how the free energy composition would look like schematically. So, the free energy composition at T equilibrium, T liquid, T liquidus, and remember the left side is, I will just put Xa equal to 1, this is Xb equal to 1, that means 2 pure sides. So, this is moving as Xb, and at T, if I try to look at the melting point variation of free energy versus temperature for pure metal, that would look like this. So, one was for liquid, another one is for, so let me do it with blue, for A, this is GA naught liquid, this is GA naught for solid, this is GB naught for liquid, and this one G naught B for solid, and that point T M A, and this point is T M B. Okay. So, we are choosing a temperature which is in between T M and T B, T M A and T M B, that means the melting points on A and B, but it is exactly that temperature exactly. If I draw a parallel line with respect to x b, composition axis on T versus x b plot, this particular T liquidus line is actually passing through 2 points, that is one point is crossing liquidus, another point it is crossing solidus line, but that crossing point of the liquidus is exactly matching with C naught. Okay. So, that case my plot pattern would be, so this would be my G B naught of liquid, this would be, just a minute, let me just check, in between we have G B of solid, and this side would be G A naught liquid, which will be assigned to 0, this is also assigned to 0, okay, at this location, and correspondingly this will be my, this will be G B naught liquid, and here let us say this is G A naught solid. So, this is basically G 1 solid, and this is G 1 liquid. And now, if I draw that particular diagram, so we will see that solidus line which is drawn with green color. So, this I am just doing it schematically. This, the another one, and this is the C naught composition, this is the C naught composition, let us say. This is the C naught composition with respect to B, remember weight percent of B. So, you will see that that line would be exactly, okay, this is G 2 solid, which is a liquid solid solution free energy, and the liquid line would be exactly falling here. Okay. So, that would be my G 2 liquid, okay. And we know that G 2 equal to G 1 plus delta G mix, solid and liquid. Okay. So, now if I do a common tangent, that common tangent will pass through this. Okay. So, the one point would be exactly matching with this C naught for the liquid, and the other one would be at C S, and this is C S 1, and this point would be C naught. So, that would be the situation. So, now you can see that a liquid solution would have a composition C naught and the solid solution would have composition C S 1. So, that is what we have written. Now, if I try to go down, let us say T equal to T 2. So, that time composition is C naught. So, then this would be my C S 2, and this will be C liquid 2. Okay. So, solid solution would have composition CS2 plus liquid solution would have composition Cl2. Similarly, T equal to T solidus, C equal to C naught, that is the alloy composition what we have taken. That time you would see that this line, the solidus line is cutting across solidus temperature, that this temperature is cutting across 2 points. One point is at this location, another point is at this location. So, let us say this particular point is CL3 and let us say this is C naught, this point is C naught, this point is C naught and this is CL3 which is this point, okay, that liquid crossing point. And at this point we will see that the solid solution would have composition C naught, but liquid solution, which is the crossing point of the temperature line parallel to composition with liquidus line. Okay. Liquid solution would have composition Cl3. Okay. You can also do a corresponding plot there. So, the corresponding plot, if I try to draw it, so the corresponding plot would be, so this temperature is also in between both the melting points of pure metals, and you can refer it to this particular diagram to see how the reference 0 point is assigned. The similar way it will be assigned. So, this is x b equal to 1 pure B side, x a equal to 1, this is pure A side, this is G 0 point which is G b naught solid, and this is G a naught liquid which is 0 as per this scale, schematic scale. So, this is the temperature I am talking about. Okay. So, here's G b naught liquid and here would be G a naught solid, fine, and composition is changing this way. So, we get one is this is G1 liquid, the another one is this is G1 solid, liquid line is this one, and the solid line would be like this way. Okay, solid line is like this. So, if I draw a common tangent, the common tangent, and this is G2 liquid and this one is G2 solid, and then that means solid solution. So, if I do a common tangent would be like this, and interestingly, if you check the solid solution, that alloy composition what you have taken, that alloy composition will, this is C naught. Okay. So, and this is C liquid 3. Okay. So, that is the composition. So, that is what these two compositions, the equilibrium compositions are reflected at this location, at these locations. So, that is what the solid solution and liquid solution would have these compositions, and that diagram, this is at T solubility, that this is solidus, and here we have T liquidus. So, that is actually given here. Okay. Now, both the diagram how free energy composition look like, so that schematically it is shown. Now, finally, at T equal to T1, definitely we will get all the composition, that C2 composition would be solid solution. Composition would be C naught. Okay. So, that is the information we can get out of it. Okay. So, now if I try to look at, let us say I look at T2, the T2, let us say I do it at T2, C B, and this is in weight percent. Okay. This is pure A and this is pure B, let us say, and this is temperature. This is the plot we have seen, and this is TM B, this is TM A, and I am trying to look at, this is T2 temperature, and the composition that was chosen is C naught. This is in weight percent. So, this is the composition C liquid and this is the composition C solid. Okay. Now, once we have such situation, then we can actually calculate the fraction of two phases. We know that here we have solid and liquid phases of specific compositions are coexisting in equilibrium. So, now if I try to look at temperature T2, we need to see mass balance of B. Let us look at. Now, if I look at a particular content of solid and liquid, let us say weight percent, weight fraction of solid equal to Ws and weight fraction of liquid solution is equal to WL. So, definitely Ws plus WL should be equal to 1. If I try to look at the combined content is 1, that means 100%. So, that then we can see Ws and WL are basically two fractions of solid and liquid separate respectively. Now, if I try to look at the mass balance of B, that is the solute or the B content, whether you take B or A, you just have to consider the opposite way. Now, if I take B, since this consideration of the composition over this T versus composition axis is as with respect to B, I can find out the composition the B content in the solid fraction. So, the B content in solid fraction is equal to that solid composition is Cs into Ws, B content in liquid fraction is equal to Cl into Wl, that is basically the B content, and the total B content in the alloy, initial alloy of composition C naught. Okay. So, that is nothing but C naught, that is nothing but C naught, okay, the total B content. Fine. The total B content should be same because we are not adding any B from outside, and also if I take the C naught composition, if I start from complete liquid solution and if I reach to T2, so then these composition will distribute into two different phases, solid and liquid solution of composition Cl and Cs as per the equilibrium condition what we have learned from free energy composition line. So, then these two Cs into Ws plus Cl into WL should be equal to C naught. So, that means B is balanced, and then we can write, and since it is like this, so we can write WL equal to Y minus WS. So, if I replace WL CS into WS plus CL 1 minus WS equal to C naught. So, then CS WL plus CL minus CL WS. So, this will be WS equal to C naught. So, then we can get WS equal to CS minus CL equal to CS minus CL equal to C naught minus CL. Fine. So, then WS equal to C naught minus CL divided by CS minus CL. Similar way, we can get WL by replacing WS in this equation. In this equation, we can get WL would be CS minus C naught divided by CS minus CL. So, that is the fraction of solid as well as liquid in that closed system consisting of solid and liquid solutions of composition CS and CL respectively at equilibrium. Okay. So, now if you see these two things are actually it is like this. So, you have this composition as CL, this composition is CS, and this is C naught, the alloy composition. So, the liquid fraction is, and this is the total distance which is CS minus CL, and the liquid fraction would be decided if I try to locate A, B, C. So, then WL would be BC by AC, and WA should be AB by AC. Okay. WL, now let us see whether it is following it up. BC is nothing but this difference CS minus C naught, and AC is nothing but this difference. Okay. And AB is nothing but this difference, which is C naught minus CL, C0 minus CL, and AC is nothing but CS minus CL. Okay. So, this is called lever rule. Lever rule, and this is applicable when we consider it as per weight fraction. Remember, this is weight fraction, that is what we are able to equate the B fraction in the system. Okay. And that gives us the fraction of two equilibrium solid and liquid solutions of composition CS and CL. Okay. So, now with this concept, so this is also can be found, this can also be found out from a phase diagram. So, that means very important informations we can get out of a phase diagram, simple isomorphous phase diagram. Okay. So, we will now look at the formulation of formulation, so that we can calculate isomorphous phase diagram from thermodynamic data. So, till then, so today I will stop here. So, we will continue our discussion on the formulation and finding out the isomorphous phase diagram from thermodynamic data in the next lecture. So, till then, thank you very much.